this last presentation before lunch, we are going to see some human-robot interaction control from the physical point of view, especially applied to wearable robotics. Is any one of you working with exoskeleton wearable robotics? Only one? Okay, good. Thank you, Serena. Okay, good. Actually, what we are going to see is quite wide, so not only applications to exoskeleton wearable robotics, but in general, the presentation is about this kind of technology. So why wearable robotics is important? So do you have in mind any application, any domain in which wearable robotics is actually important? Can you say something? Medical, for example, rehabilitation, medical. Any other domain? Agriculture, perfect. So in general, construction, rescue, industrial, so basically whatever you prefer to work in. And actually, yes, so we need to provide assistance to humans in order to actually perform better the task they are performing. Can be again industrial, so we need to in a way augment, but better to relieve the human from the effort of the task. Healthcare, rehabilitation, medical application, we want to restore the ability of the human for mobility. Rescue, again, we want to basically assist the user in the difficult environment in which he's working. And similar human augmentation, we want to provide better performance for the human. But if we consider wearable robotics instead of autonomous robotics, what are the differences that you can identify in this domain? So why it matters to take into consideration especially physical AI for wearable robotics and not in general for robotics. So what is the difference between wearable robotics and autonomous robotics? What can you imagine? So humans are random, we need to be specific to tailor to the human. Something else?
The commanding itself, autonomous can be fully autonomously command, but wearable, like there is a human action involved.
Yeah, so in general you are physically connected to the robot basically also, no? So in principle, what it changes is that we cannot anytime stop the contact with the robot. So we are always in contact, we're always in interaction. So safety is the first issue that we can highlight in this context. So while in physical human-robot collaborative robotics, we can always step down from the contact, we can always move back, and we can leave the contact with the robot, in wearable robotics we cannot basically. So this is an important aspect of this domain of application of robotics. And then for sure what else we said. So we need to tailor our assistance, our collaboration, interaction with the specific human. We need to understand the human intention of motion. We need to understand the environment. And then we need therefore to reason and to take actions in this context. So specifically related to exoskeletons, until now what we can identify as collaborative, let's say, solutions, so physical human-robot interaction solutions. Usually exoskeletons are equipped with different sensing solutions, especially related to the human. So we can sense, for example, the EMG signals, so the muscular activity. We can sense the interaction forces. We can, in some cases, also perceive the environment. But what is still not really available is how to use all these informations in order to take actions, reasoning about the environment, and then take actions to coordinate the interaction with the human. So basically we are blind to the context, usually many times, in which we are operating. Also, if we take into consideration the last exoskeletons that have been developed for human augmentation, basically are just based on a reactive control. So we measure interaction torques forces, we measure accelerations, and then we adapt the controller. But this is purely reactive. We cannot basically predict or plan any action based on the context in which we are working with. And this is basically the main point of physical AI taken to exoskeletons. So we want actually to take all the pillars that are in physical AI for autonomous robots and try to understand how we can translate these to wearable robotics and therefore also to physical human-robot collaboration. As we said, the main difference between physical human-robot collaboration and exoskeleton is basically the contact that we cannot basically leave anytime. And therefore, if we are able to take all these pillars that we are going to see into physical human-robot interaction, actually we can improve the performance of collaboration. So as we quickly said, nowadays classical control pipelines are basically purely reactive. So exoskeletons are sensing joint angles, CMG, forces, accelerations, and then are using this information in order to design a controller to inform the controller that is reacting to these signals. But what is, for example, a limitation about this? So what can you imagine that is resulting as a reduced performance if we just purely react to the human intention related to forces, accelerations, and so on? So let's say you want to, even with a collaborative robot, you want to operate a robot, for example, in teaching by demonstration, so you apply a force, the robot will follow the force, basically, right? So what is a limitation about that? Yeah. Latency, for example. In general, the delay that is introduced by the dynamics of the system and the control dynamics, basically. So you are always basically late with your control action. So the idea instead is try to be proactive and try to anticipate the need of the user. For sure, as we said before, in this case, we always need to be safe. So anyway, we should have a safety layer, double checking every time that what we are controlling is consistent and so on and so forth. But the idea is trying to be proactive. So we can sense the environment, we can have a vision system to understand the environment, to perceive the environment. We can even reconstruct this environment, providing it with semantic labels, and then we can use this information to reason and understand the environment, to plan control actions and also to plan high-level tasks like path planning, for example, in rescue tasks. And then we can apply these to the exoskeleton to assist the human. So in such a way we can try even to be really real-time, because we can understand the environment anticipating the need of the user, always guaranteeing safety. So this is basically at the basis of this recently founded project, PHYS-EXO, in which we want to try to combine all these pillars into wearable robotics, but again, can be related to any human-robot interaction environment domain. So the idea is indeed to combine perception to identify and perceive the environment in which the human and the exoskeleton are working. We want also to reconstruct the environment, providing a semantic understanding of this environment, and then we want to plan tasks and control actions in order to assist in a proactive way the human. So instead to be purely reactive, to be proactive, let's say. So starting from the first element, perception. So vision-based control approaches have been developed since some years in the wearable robotics domain. And the idea is basically to increase the data, the sensing information that we have, also with additional sensors that are not only measuring the human state, basically. So like interaction force, CMG, IMU, and so on, usually are basically trying to predict the intention of motion of the human, and then the controller will react. In this case, what we would like to do is also to understand the environment in which we are operating, classifying it, and then take actions that are better for the task that we aim to execute. So that in such a way we can be again kind of proactive. One of the first works in this direction was done with the group of Lorenzo Masia, especially by Enrica Tricomi, in which for this exosuit was applied a camera to detect the environment, classify the environment, and this information was used by the control in order to select the proper control strategy and control gains to maximize basically the performance. So in this case, what we were doing is basically, first of all, environment classification. Are we walking on a stair? Are we walking on a flat terrain? And then this information is provided to the low-level controller to select the proper, basically, control tuning and assistance to be provided by the exoskeleton to the human. And therefore, first of all, a training of the convolutional neural network was done in different environments, in different scenarios, incline-decline stairs and flat terrain, so that we are actually training our algorithm to classify, detect the environment in which we are working in. After that, these informations again are used for control purposes. So all we are doing is basically devoted to the control of the exoskeleton to maximize the performance of the collaboration between the robot and the user. What we can see, just quickly, some results are related to the performance of environment classifications, which are quite good, and then also related to the performance of the human exoskeleton collaboration. What we can highlight is that with the exo off, so no exoskeleton basically, the effort of the human is higher with respect to the vision on, which is basically the full vision-based controller able to classify and provide assistance. In the middle, what we have is the exoskeleton with vision off. It's a kind of, how to say, trade-off between all the different environments, and for sure it is suboptimal. It is able to provide some assistance, but not tailored to the environment in which the human and the exoskeleton are working. And this actually can be applied to any kind of application, even collaborative robotics. So you have a robot that has to interact with the environment, you need to perceive the environment to classify, for example, objects, just even for the payload, and then understanding the payload, applying the compensation, and then assist the human in a better way. But in this case, what is actually missing is any environment mapping and understanding. So we are just classifying the environment. We just have a very simple classification, so basically declining, inclined and flat terrain, and then we just, like in a lookup table, select the control gains that we need to apply to the controller. But what if the environment is much more complex? So let's take an example of a rescue task, a completely unstructured environment where we have different risks, where basically we don't know anything about the environment anymore because maybe there are some collapsed areas, fires, whatever, and then we need basically to detect what's happening in the environment. We need to understand what is happening, what are the risks, and then we need to take decisions about these risks. How to assist the human in the best way possible, for example, to go from a point and reach a victim that is related, that is basically needing for help. So in this case, what's important is the ability to reconstruct the environment and the ability to reason about the environment. So how we associate a semantic understanding of what's happening into the environment. So some interesting works, even not applied to exoskeletons directly, have been done for sure, and one of the most interesting was presented by a colleague from EIC at AIxHRI 2026 and was applied to a nanodrone. So why do you think this work, even if it is not directly correlated to exoskeleton, is actually very important to this scenario? So why a 3D environment reconstruction applied to a nanodrone is actually very important for a rescue task with exoskeleton? Any idea?
Because we give the map of the environment to the exo.
Yes, but from the, let's say, constraints point of view, computational constraints, onboard computation basically. So nanodrone, do you know what I mean with nanodrone? Can you imagine? Yeah, it's a very small nanodrone with all computation on the edge. So all computation on the edge means that the reconstruction of the 3D environment has to be done on the edge, which is difficult, I mean. From the hardware and computational constraint point of view, this is a huge problem. The same can be basically resulting in a rescue application. So in a rescue application, you might be indoor, outdoor, but there might be basically disruptions into the city, infrastructure, whatever. Especially if you are indoor, you cannot even have any connection to the internet, so you cannot rely on cloud computation, for example. So you need to have all the computation capabilities on board, and then you need basically to just rely on that. You cannot access any infrastructure outside. And in this case, it was quite impressive to me to see how this reconstruction of the environment can be done on a very small nanodrone with a very small computational power. So the idea is that even if images are much more blurred than in reality, but we are even able to reconstruct a 3D environment that can be in a way used by the control to detect what's going on, classify, understanding, and then providing actions to the hardware, to the robot. So in this case, only 3D reconstruction was done. What is missing to go to the next step is basically semantic understanding. So we can, for example, even in the reconstructed environment, recognize the cones, but we are not even providing it the frames to a semantic meaning. So the idea is, once we reconstruct the environment, especially in a 3D settings, we understand where the objects are, we understand how the environment is built, we can associate with the pixels and especially with the spatial informations of the environment a semantic meaning, and then we can therefore take action. So we can locate, for example, a risk. There is a fire, there is a collapsed part of the building, whatever, we know where it is, we know that is a risk, we can take actions based on the risks. Similar to this, even if it was done not on edge, we developed this, starting from a previous paper, we developed this Gaussian splatting based framework in which we are able to reconstruct an environment and associate into the environment, and especially to the 3D reconstructed environment, the semantic meaning of it. So for example, this is a scenario related to a kind of agricultural domain. So we want to reconstruct a lemon tree. We want to also locate the lemons in order to be picked up by the robot. We're actually able, with Gaussian splatting, to reconstruct the 3D environment and then to locate, associating this meaning, semantic meaning, to the lemons, so that we are able actually to perform our task. So we know where the tree is, we know where the lemons are, we know where the leaves are, and we can actually pick the fruits without, let's say, or being safe, let's say. So the idea in this case, and that can be applied to the rescue environment, is really to reconstruct the environment and then basically masking the important elements that are present in the scene, locating them, and associating them with a semantic meaning. So like in this case, we tested on many different plants, lemons, sunflowers, and so on and so forth. And you can see all the steps of the algorithm. So starting from the RGB images to the reconstruction of the 3D environment to the extraction of the important elements with their associated semantic meaning that we can use to plan, reason and plan our target task. Again, in this case, for the lemon tree, was related to picking the lemon, basically. And all these informations coming from perception, 3D environment reconstruction, and semantic understanding can be used then in task planning for exoskeleton in this presentation, but in general for any kind of robot, collaborative or autonomous. So once we have a reconstructed environment, once we have a semantic meaning of what we are seeing in the environment, we can actually use these informations in order to provide the robot with a plan, and actually multiple plans. Multiple plans that can be evaluated based on metrics, for example safety, so that we can take the best option coming from the reasoning layer. So in the exoskeleton domain, and in particular in the rescue task, all these plans are not then autonomously executed, are provided to the user, to the human, that is always in charge of selecting or approving the target plan. So as always, when we speak about human-robot collaboration, the human has to be in control of the task. Final decision is therefore done by the human, and therefore these are basically proposals provided by the AI layer to the human that has to approve and select finally. So what we can do, especially in exoskeleton domain, is to provide informed task planning to the human so that she can decide what is the best option based on the metrics, on the reasoning, and therefore we need for sure to have also a trustworthy algorithm with explainable AI approaches that can provide all the information for the human. So something in this direction, even if not directly applied to exoskeleton, has been done by Alessandro, that is in the audience, I hope. He's not sleeping anymore, so he's here. And what he did was basically to develop this approach for reasoning for robots, autonomous robots in this case, especially from a safety point of view. So understanding the risk and then taking safe decisions, especially in the task planning design, so that the robot can execute the given task by the human in the best way possible. So the human basically, as ChatGPT provides a prompt, a target task to be executed, we have the OPE layer, which is basically, maybe I can also switch. We have the OPE layer, which is basically extracting all the informations come in the environment that are coming from a perception layer. In this case, a YOLO algorithm that is extracting all the objects with all its properties. So the idea is that in such a way we can understand, for example, if an object is dangerous, if it is fragile, or whatever property it has, and we can inform the URP layer with these properties so that basically we can provide the planner with all the informations related to the task and to the objects that are present in the scene. And then the planner can basically provide the robot, or in the exoskeleton case, the user, with multiple plans that are ranked by scores, for example, the affordance or LLM score, related to both the safety, so risk-aware planning, and in general to the target actions goal that the robot has to achieve. And in such a way, we can, for example, avoid these kind of issues, in which we asked the robot to put all the food into the bowl, but actually the standard LLM doesn't understand that the glass container is dangerous for the bowl itself. With the advanced, let's say, safety-aware, risk-aware planner, actually we can detect that there is food inside the container, but the container is fragile, the bowl is fragile, so we don't need to throw the container into the bowl, but we can provide it to the human beside, in front, with respect to the bowl itself. So similarly, what we can see here can be applied to exoskeleton, physical human-robot interaction, any domain you like. And the idea is therefore to embed safety, risk-aware reasoning into the control of the robot, task planning of the robot, so that we can actually improve the execution of the task. And then finally the last layer is anyway the physical human-robot interaction control. So again here the controller that is traditionally based only on measures coming from the human exoskeleton interaction can actually benefit from the improved information, enhanced information that are coming from the different layers. So again, the perception, the 3D reconstruction and mapping, the semantic understanding of the environment, and then the task planning can basically provide a set of informations to the low-level controller to improve the execution of it, and therefore the physical human-robot interaction performance. So we started many years ago, much more than I wanted to admit, to work on physical human-robot interaction control with collaborative robots and then with exoskeletons. And the first approaches we developed were related to model-based reinforcement learning variable impedance control, and especially in this kind of case, the controller is again purely reactive. We have a state that is monitored between the human and the robot interaction. We use this information to train an ensemble of neural networks that are used then into an NPC, and then the NPC is basically providing the next action to the robot, reacting to the current state of interaction. So basically the current state is based on position velocities and interaction forces, and the NPC is computing the best set of control actions, in particular in this case the stiffness and damping of the impedance control, to maximize the performance of the collaboration. In another work, we combined, and I'm glad to show that preference-based optimization is interesting, we combined this kind of approach with preference-based optimization. So preference-based optimization is actually quite powerful, especially for physical human-robot interaction, because we can basically rank the different control settings based on the preference of the human, so that we can optimize their tuning and we can be basically more efficient. So especially considering preference-based active preference learning in physical human-robot interaction domain, why do you think it is worth to apply that and not any other kind of quantitative optimization approach? So quantitative means what do we need? Are you familiar with Bayesian optimization, for example? Reinforcement learning in general. So what do you need when you design, let's say, traditional RL approaches or Bayesian optimization approaches? You define what?
You need an objective value.
So you need to design the reward finally, basically. In the Bayesian optimization, the cost function. But this cost function has to be quantitative. So what does it mean, quantitative? Sorry? Yeah. You need metrics, you need KPIs. KPIs are usually coming from any sensor that you have, any user-based, again, metrics that you can combine into the cost function, and then you can basically do the optimization based on that. If the cost function is wrong, the optimization is wrong, and especially in physical human-robot collaboration, for example, some metrics that you can define are related to EMG, for example. So you want to minimize the muscular activation of the human to reduce the effort. The problem is, for example, with EMG, that EMGs, are you familiar with EMGs? Okay, more or less everyone. So where you place the EMGs will affect the matrix computation. If you change the human, will affect the matrix computation. So you always have basically thresholds to fine-tune, let's say, by hand. And therefore, quantitative optimization for physical human-robot collaboration is not so probably powerful, but instead it is preference-based optimization. In preference-based, as we saw in the previous talk, we need a qualitative feedback from the human in order to rank basically the different experiments, tuning settings of the control parameters. So in this case it's actually quite powerful, because I can immediately say if I prefer one setting or the other, but there is also a con. What do you think is a con that was also mentioned before in the previous talk in this case? What is a big limitation of preference-based optimization into physical human-robot interaction optimization? So if you perform, for example, 20 experiments, can you trust yourself in the evaluation of the last with respect to the first? It's difficult to recall. So if you have a visual feedback, it's easy, but if you just have to rely on your memories, then it's not so easy. So the consistency of the judgments coming from the human is in this case very, very important, and it's a drawback. So you have to, anyway, consider this as a problem when you run this kind of optimization in this context. But anyway, we were quite successful in this, and preference-based can be a powerful tool, especially for physical human-robot collaboration, where you don't have to anymore design any metrics, any cost function, but you can just rely on the feedback, qualitative feedback of the human. Then what we can also think about are end-to-end controllers, end-to-end models. In this case, again, a work of Alessandro, where we are fusing, let's say, images and forces together with demonstrations coming from the EMG to vary, to adapt the impedance parameters for the controlled robot into a diffusion model. So in this case, the idea is to take demonstrations, that are coming from the human to train a model that will mimic basically the target task, adapting also the compliance of the robot. This is especially important in contact-rich applications where we actually need to adapt the interaction and the stiffness of the robot during the interaction. And then something similar was done by a master student, in which we trained again a diffusion policy to, in this case with a collaborative robot, to make a collaborative robot a follower of the human, which is the leader of the co-transportation task. And in this particular case, the diffusion policy was not trained directly on RGB images, but on the exoskeleton extraction with, I don't remember the tool now. I will remember later. The idea in this case is therefore to try to be general into the training of the diffusion model so that we can be, again, more general in deploying. So what is, in your opinion, the main limitation if we train with RGB images only directly the diffusion policy when we then deploy it to the real robot? The camera can change, and in general, what can change is my t-shirt. So the trained policy will be affected by the RGB images that we are using in the training. In this case, instead, trying to, let's say, standardize the images that are used in the training, then we can also standardize the deploy and therefore be robust, be actually agnostic with respect to the background in general to the pixels. So in this case, the powerful, the power of this kind of approach is that in the case of the diffusion policy, not only trained, for example, based on the forces, but trained also based on the skeleton, the posture of the human, will allow the robot to predict in advance what is the intention of motion of the human and can also move without any force applied to it. So if I collect a dataset which is rich enough, for example, moving first my body on the side and then pushing the robot in deploying in inference will understand that this motion, even keeping the hands fixed, will mean that the human wants to move on the side, and therefore with vision we can predict the intention of motion of the human, and we can be proactive and not only reactive in terms of interaction forces, which is instead what we do basically with admittance or impedance control based only. So in this case, the interesting stuff is to understand from the point of view of the images what the human is going to do, and therefore try to have a proactive behavior of the robot to follow and to, in a way, anticipate the intention of motion of the human. And then finally some remarks on the computational requirements, as we said before, so very quickly. We basically, especially when we are considering exoskeletons, we need to have the most that as we can on edge, so that we can be in general robust, safe, and unconstrained with respect to what are the infrastructures, the external infrastructures, and this is especially something important if we work in a rescue or similar application where we might not have this kind of infrastructure anymore. And therefore what we need is to have models that are small enough to be run and even updated on the edge, and then for some other applications like medical or industrial, we can still rely on some cloud-based computation. But in principle, we should always have the minimum layer of intelligence and especially all the safety on board, because in this particular domain and applications, this is very critical. So if we lose, for example, the connection with the outside, we still need the exoskeleton to reason and to act in a safe way with respect to what is the task and especially the human. So very quickly, some current developments applied to exoskeletons that we are doing in the lab. We are working with this back leg support hip back support exoskeleton that we have in the picture. It was developed by us in 2021, 2022, more or less, and we are using this as basically a platform to test and deploy our algorithms. So it is a 3 degrees of freedom exoskeleton. We have 1 degree of freedom with 2 motors that are working in parallel for the back flexion, bending, and then we have 2 for the hips. And then we are going to add 2 passive degrees of freedom for the knees. What we have for on the edge computation is a Jetson or a Nano, and then therefore we would like to be independent as much as possible from outside computation. And then again Alessandro developed this vision-based control that is using indeed the Tobii Pro 3 glasses, which have an integrated camera in the frame, infrared sensors to detect the gaze of the human, and therefore we are using this information in order to understand the environment, perceive the environment, but also to predict what is the intention of in the task of the human. And just a quick video, if you don't know what Tobii glasses are, let me see if it is working. It's not working, so if you want to better understand, let me know. So what we have therefore done is, starting from the low-level controller, I'm still a mechanical engineer, so I like model-based control. So we have variable admittance control at the basis of the exoskeleton. This is providing a control compliance to the exoskeleton. And in particular, we have a term that is related to the assistance for the compensation of the payload that the user is lifting. Then the second layer is a finite state machine block, which is basically based on a YOLO detector, where we do not only classify the object that is in the scene, but we also classify if the object is grasped or not. So the idea is that by understanding how the operator hands are positioned on the object, we can also understand if the object is manipulated or not, and we can compensate, therefore, the payload related to the object. To do that, we also use the gaze that is not really visible, but it is this red circle to understand if the human is looking at the object or not. Usually when you want to manipulate something, you look at the object, and therefore we associate to the frame, to the image, also the point of view of the human, and therefore we update the finite state machine. And then the last layer is the high-level, let's say, perception module, in which we have again a VLM based on YOLO. We use the gaze, for example, to disambiguate between different elements, different objects in the scene, so that we can basically preload the related payload into the control and then apply it in the specific state of the finite state machine if needed or when needed. And this is basically one example of one task, one experiment with this control architecture. We can identify the box not grasped and then grasped, and using both the camera in the glasses frame and the gaze of the human, and then we can modulate the assistance of the exoskeleton during the task execution. Okay, just quickly finishing, what's next? So, for sure what we need to do is to bring all the pillars that we have seen into the exoskeleton, especially on the edge, and to do that we need for sure sensor fusion. So for now we are relying purely on RGB cameras, but infrared cameras, other type of cameras can be actually very, very interesting to provide additional information, semantic understanding to the scene, and therefore improve the reasoning side of our intelligence layer. Risk-aware reasoning, again, we did some works in autonomous robotics, and therefore we need also to take this into our exoskeleton. Human-centric assistance, similar to that, what we have done so far is a disconnected preference-based optimization for exoskeletons or human-robot in general interaction tasks. We need to connect with all the other layers in order actually to be fully connected and proactive. And finally, what's also interesting is to coordinate other robots with the human and the exoskeleton, so that, for example, we can make use of the drones, the quadrupeds or whatever to reconstruct the environment and also to take action for us. And indeed, so beyond exoskeletons, we can apply this kind of framework to anything we want. The framework is designed to be modular, to be independent, agnostic with respect to the hardware, and therefore basically once you have a 3D reconstruction module, you can apply to any agent that you like, the same for the reasoning and the task planning. Okay, thanks. If you have any question, let me know.